Another probabilistic planner is an RRT, a sampling-based planner, rapidly exploring random trees. This is a single query planner to get from configuration A to configuration B. And the idea is to randomly sample Q-free for a path from Q start to Q goal, growing a tree, not a graph, towards the goal. And what's nice is we can use two trees, one rooted at the start, one rooted at the goal, and hopefully they will merge and make the path efficient and fast. And eventually the trees grow, they share a common node, and they're merged into the path. So how does this work? Well, here is the build tree algorithm. So let's take this group of obstacles, and we're trying to navigate from a start to a goal. And you can see the start is the root of the tree. So we'll start there. And then at each step, we're going to generate a new random configuration QRand. And so you can see we've built a few nodes of the tree already, and now we generate a random configuration QRand, which is the red dot in the image. We find this nearest tree node. So this is where the nearest neighbor computation is important. And again, the distance function between the two nodes is used to find that nearest neighbor. And once we find that Q is the nearest tree node, then we move along the path QRand, that straight line, a distance step size, which will create a new node QNew. Okay? So hopefully we'd like to go all the way to QRand, but basically that's too far for the local planner, so we go a small amount of distance and check. So we find configurations which are somewhat close to each other, but the direction is forced on our hand by QRand, so it could be an arbitrary direction. And then we repeat this. And you can see the tree will continue to grow each time by generating a new random sample, okay, finding the nearest neighbor, connecting to the tree, and moving out a step size from it and growing the tree by a little bit each time. So here is an example of an RRT growing in action, if you will. On the left, you can see we have the tree starting to be built. We expand the tree one node at a time from the start node. Okay, and it continues to grow. We randomly generate a new sample configuration each time. We try to connect the sample to the nearest node in the tree. We go out a step size once we connect. And we create the new node. And the local planner is invoked here to find this new node that's a step size out. And you can see on the right, it continues to grow and is starting to grow towards the goal. So here we see the final event here where the tree has been built and the tree has reached the goal, and once the goal is reached we can just go back by apparent links to each of the tree nodes and find the right path. So basically following back from the goal to the start, we find a path which has reached them. And you can see it's random and stochastic, and it can spend some time in places that aren't too interesting or too useful, but effectively it will eventually find the path from a probabilistically complete standpoint. So once the tree reaches the goal, we have the path. The path is not optimal in any sense, as you can see. It's stochastic, so it has a lot of randomness to it, but it does give you a path. And this is important in path planning in higher dimensions, where it may be very difficult to find any path at all. So this will give you a path, and then after you get the path, then you can use methods to try to improve the path, and we'll talk about that too. And again, it's stochastic, so the path can be different each time between two nodes. So if you say go from A to B, you'll get one path. Another time you may get a different path. And again, as we said, it scales to higher dimensions. So we talked about how to build the tree. We haven't talked about how to reach the goal. So again, you build the tree from the start and you explore this space, but you hopefully want to get to the goal. So one way is as we add each new node, QNew, we see if it's within the step size of the goal. And if it is, we can see if we can add an edge between QNew and QGoal, which means we're not too far away. We can use the local planner, and hopefully we can connect right up to the goal once we get close to it. Another way to do it is to use a bias. QRand determines what direction we go. So we randomly could do a configuration, and that's find the nearest neighbor on the tree and move in that direction from that nearest neighbor. But what we could do is, what if the random direct configuration we choose is the goal? Okay, so you can see here, normally we have the red QRand, which moves us out to this node Q, which is the closest node, and then we go out a step size to create Q new. But notice we could have chosen the goal as QRand, which would say let's move towards the goal directly. Okay? It's a greedy algorithm though, and it can get stuck in local minimum. So if you always go to the goal, and we'll show you an example in a minute, it's not going to work. But one trick that works pretty well is you can use the goal as QRand just some of the time. So every now and then you say, let's get lucky, let's get close to the goal, and use the goal as the place we're shooting for. And if you use just a 5% bias towards the goal, you can really improve performance. There's no guarantees here, but the idea is that it's good to have goal-directed or shaping of the tree towards the goal, but not all the time. If you go all the time, you get too much bias. And this is the problem we see here, where we have the start and we go into the goal each time and we get a nice path, but then we get into this point where we can't really get out of it. And this is where the randomness overcomes these kinds of problems. Because the random tree search, you're going to move anywhere in this space, and only every now and then would you want to bias it to go to the goal and think you get lucky. There's another way we can do finding a goal, is a bidirectional RRT. So we'll use two trees, T1 and T2, one rooted at the start and one at the goal. And to connect the trees and form a path, we'll expand T1 randomly, adding a new node Q new. We'll expand T2 towards Q new. So every time we get a new node from one tree, we use that as the goal for the other tree, okay? And if tree T2 connects to the Q new from tree T1, the path is formed, and otherwise we'll just add a Q new for tree T2, which is out a step size towards Q new. And we expand the tree to Q new and tree T2, and we keep swapping T1 and T2 for expansion towards the other tree until they meet. So you can see here we have a start T1, a goal T2, and we keep building these trees, and eventually we get to a point where Q new, okay, was added to tree T1, and at that point then that becomes the goal for tree T2, and Q new, we can go find its nearest neighbor as Q2, and then we can see we can create a link, and now we have a path for this bidirectional RRT. These are just a couple of examples of showing you how this works, and again, these paths are not optimal, but they are useful to find pathways in very difficult spaces. So here we have to move on the left this vertical rectangular object through this small gap to the position you see at the bottom where it's on the other side through that little hole. And you can see on the right, some of the configurations that have been used and then tried, and then you can see the path that we actually come up with. Here's another example where it has to go through a tight area and chooses configurations to get a path. Now, one thing also is we said these paths are not optimal. We can try to optimize them and do some smoothing on them. So the first thing is to try connecting non-adjacent configurations. So you can see in this graph we have the dots are the original path, which is kind of herky-jerky, not straight line, which we like, or optimal in some sense. And what we can do is we can just take every other vertex along the path and see if we can connect them up. So if you see we have the first three vertices in the original path, well, we can take 1, 2, 3, we can take 1 and 3 and see if we can connect them up. And that'll bypass 2, and that's, you can see what's going on here. And we can choose 2 of these vertexes along the path randomly and try to connect them. And the greedy approach is trying to connect directly to the goal, but that's a little too greedy. But the idea is you can make the path more efficient afterwards by doing these optimizations. So let's summarize RRTs. They're an efficient way to form goal-directed search without explicit computation of the free space. Okay, so we're just sampling the C space and we can find configurations that are free, but we don't know all the configurations. It scales nicely to higher dimensions, which are difficult to do exactly. We can use approximations here by doing sampling of this high dimensional space and find regions which we can navigate in. and it's good for multi-degree of freedom robots. The performance is somewhat related to the local planner, because every time we get two configurations, we do have to check to see if there's a collision between them, and that can take time. And the step size is another important parameter which affects how far the local planner has to search. The nearest neighbor computation can slow performance because, as you can see from some of these RRTs, you have thousands and thousands of nodes, so nearest neighbor becomes an important computation. You have to find the nearest neighbor efficiently. One nice thing about RRTs, and we won't have time to talk about them today, is that they can be used in what's called kinodynamic planning. You can also include in velocity and other constraints in building these trees. So in all these cases, we're talking about basically kinematic changes, position and orientation. But we might also have constraints which are kinodynamic. There might be velocity constraints. So for example, suppose you want to park your car, okay? You want to find a path to move your car from adjacent to one car into a parallel park space. And we know that that's not a simple thing to do for a path planner. A car is a non-holomorphic device, which means you can't move sideways with it, so you have to figure out a path and a plan. And in fact, using these planners, you can do that. Now, you may get a herky-jerky path, which will back you up and turn you around 3 times, but eventually you will get into the space because you include the velocity constraints and also turning constraints in that to use these kinds of planners. So they have the ability to work with more than just kinematics. There's a great website on RRTs. You should go to it. It gives you a lot of animations and more detail than we have time for today. So let's summarize what we talked about today. There are many methods of path planning to choose from. And really, the one you want to choose depends a lot on the dimensionality of the configuration space and the application. There are trade-offs. There are trade-offs in computation time, accuracy, optimality, and safety, and you have to weigh these with your problem and your application to see which is most important, okay? If you're out in the prairie, you don't have to worry about running into things. If you're in the city, you do. So it depends on where your planner is being used and for what reason. Most of the methods we talked about today are purely kinematic, okay? They do not incorporate dynamics. Particularly we talk about humanoid robots. We have a real problem. We can plan paths, okay, for a multi-jointed bipedal robot, but it may not be realizable if the robot will fall, if one of those configurations is where it falls and it's on the ground, okay? So we want to be able to have robots move with other constraints. In this case, there's a constraint due to stability and gravity. So how do we include that? Well, we don't have time to talk about all the methods to do that, but one simple solution we can do is we can find kinematic paths between known stable robot configurations. So what you can do is you can restrict your configuration space where you're sampling to known configurations which are upright and safe for a humanoid robot. And you might have ones where, if it's a bipedal robot, where it has one leg in front of the other and so on, so you can kind of find positions where it can move efficiently from one configuration to another. Once you do that, that becomes your configuration space, okay? And you don't have to sample a lot of obviously bad configurations. You want to just try the ones that you know seem to be reasonable. And now, even if you do that, you get a kinematic path, but there's no guarantee that it's going to be stable, because between configurations which are known stable, it may be unstable. So what you can do is you can add a dynamic stabilizer, much like a local planner, to smooth the resulting kinematic path and ensure stability. So you can think of this as a 2-part planner where it does a kinematic plan and then a dynamic plan on top of that. And this is very important to remember, particularly with humanoid robots. The paths may not be smooth in Cartesian space, especially true with the sampling-based methods. So for example, if I'm a robot and I want to move from this configuration to that configuration, okay, it seems like this would be a nice smooth way to do it. But if I use like an RRT or some other sampling-based planner, if I go from this configuration to this, I may do all this and then get to this. So we have a lot of extraneous motion that we sometimes have to get rid of. So these are things to consider when you do path planning, for robots particularly. Okay, thank you very much.